Let us begin our session, today's session. So we are trying to understand some basic concepts of fluid mechanics, though the animations, the visuals, these things looks quite fancy and nice. One requires a quantification of those terms. Something like there is an automobile car over which something is happening, some kind of crazy random kind of stuff is happening, motions. It's always be good idea to quantify what is that, how far they really extend, how much force they will impart, or how much energy they will really take out the system, and so on, so kind of stuff. We require little bit language skills. Instead of just having English language skills, here we talk in terms of math. This means this is the way we will quantify. Maybe for example, here I'm showing you a river which is trying to change its direction, some kind of meandering. Now saying something like it is some kind of wavy path is different. It is having this kind of particular amplitude, this kind of particular wavelength, this many waves are superimposed to really construct that. The typical width is so and so kind of stuff and so on. That is what we call quantification. And for that purpose, we formally introduce few terms named streamlines, streak lines, path lines, something named stress field, pressure, and so on, so kind of stuff. So to do that, the first thing what we do is try to give two perspectives named Lagrangian frame and Eulerian frame. Like I said in the last class, if something like I'm breathing in, breathing out, billions of air parcels or particles are coming in, coming out. This particle, if I use a word, means much bigger than molecular level and much smaller than room size or perhaps my nose size or perhaps my lung size and so on. So that kind of continuum limit where I can really talk infinitesimal elements, those are the ones what I call particle. They can be 1 millimeter size, they can be 1 micrometer size, they can be 1 meter size, depends on what kind of problems I am trying to look at. If I am more interested about lungs and so on, so kind of stuff, the typical dimensions, trachea and so on, so things maybe 4 millimeters, 5 millimeters kind of thing. So the particle size might be 5 micrometers, maybe 1 micrometers and so on, much bigger than atomic and molecular sizes. If I'm talking about oceans, this particle size might be 1 meter compared to 1,000 kilometers. So something very infinitesimal, we call it as particle. And let us consider there is a bridge. You are looking from top view, and that bridge contains a lot of pillars. One of the pillar, what you are trying to look at is that from top. River gush is happening from left side towards right side. So river gush is happening, fluid particles, if I am thinking of thousands of things, are traversing across this bridge, the pillar. So flow really comes over the pillar, it just takes turn and goes and so on, so kind of stuff. So each of these fluid particles possess certain momentum because they are getting displaced from one location to other location. So naturally they might possess some velocity. Maybe as they are traversing from one location to another location, maybe they change the direction, they may accelerate, they may decelerate and so on. So they naturally possess certain amount of force on them. Each individual particle perhaps possessing different kind of forces. With all those forces, it might be trying to strike this bridge. Maybe some of these fluid particles may not be striking, they might be just passing over it. While they are passing, each of these particles try to impart momentum on the local neighborhood. So ultimately, all that momentum faced or seen by this pillar also. If this pillar is not strong enough to overcome these kind of forces, perhaps the bridge, perhaps the pillar, it might be sheared. Sheared means broken into two pieces or cut into two pieces. Some of the things are trying to really strike it, some of the things are going to have less momentum, so it might really bend, cut into pieces, or perhaps it might be squeezed, bend in that forward direction, finally broken into pieces. Many kind of things happens. So any design which really try to have that kind of stuff, one has to really calculate how much force imparted by these particles. Maybe the easiest thing what one can really think of is, rather than individual particles striking the bridge, the collective effort with which it is trying to apply on the system. And that kind of stuff, what usually fluid mechanics interested in. If we are going to really look at the collective effort, then we call integral analysis or integral effort. If we are looking at individual particles striking it, we call differential analysis or differential mechanics. So first we begin the differential, that means we focus only on one and each of these particles. Then perhaps once we picked up that, try to learn this stuff and so on, then we move on to integral effect. So the first thing in that differential concept, one has to really understand each of these particles, how they are traversing. What might be the equation of motion for each of this red particle? If I'm going to really work it out, we call that one as Lagrange approach or Lagrangian mechanics. It is more or less similar to your +2 kind of science, where you thought only it's a bat. Maybe it might be just a badminton court. Perhaps it might be a tennis ball. It might be a ballistic missile. Only one point you try to understand that. Here, that kind of stuff we are going to look at for billions of particles. That is the only thing. The question is, these particles can interact with each other, they can really rotate from each other, and many kind of things happens. They might even get stretched up also. They might be squeezed up also. This kind of things are possible. However, writing such kind of infinite number of equations, because billions of particles are going here and there, tracking them is not easy task. However, we can apply Newton's equation of motion very clearly on these individual particles. There is other approach. Maybe don't track each and every individual points, but maybe just stay at one location. Take something like a filament, try to poke into that liquid. Maybe you heat that filament by using battery or whatever. Whenever flow current really comes, the heating component, whatever heat, that will be carried by fluid and leaves away. So naturally, there will be change in resistance happens in that probe. And you measure the change in, calibrate the change in resistance with respect to how much flow happening. So in that way, one can measure what is the velocity of the system. Especially in liquids, you keep something like a probe, which is having a tungsten filament kind of thing. You have a battery to heat it. So it is continuously heating resistance. So it is generating heat. You know how much heat is getting generated. I square RT kind of formula, you can really do that. Now liquid flow is coming, that is grabbing the heat and going away. Suddenly temperature really drops down. You calibrate the temperature, then you know how much resistance change, then you backtrack it. Okay, this is the velocity with which it is the liquid moving at that particular location. Now change the probe location from there to some other location, some other location, some other location, or install multiple probes. So you track it through your computers, whatever means, you will get the velocity. No, Raja, that's not the better way. Maybe you sprinkle particles, aluminum kind of particles, mica kind of particles, or colored kind of particles. You shoot lasers. It reflects back. You calibrate it sophisticated way. You know with which that aluminum particle is traversing. Then you will call it as the velocity at that particular location at that particular time is this. Now you would like to really find some other way. Maybe you use your autographs kind of techniques where you shoot sound signals. They reflect. Based on that, you can really sense, calibrate it. This is the velocity with which it is going. Maybe I'm the person who is walking. Maybe traffic constable can really shoot. Maybe I'm going in a car. He can really shoot a laser kind of thing, electromagnetic wave. How it really reflects back based on the Doppler effect, one can really measure my velocity. Maybe I am going to keep two such kind of measuring instruments, two locations, measure velocity at that location. Again, the same person, when he is traversing at other location, measure his velocity, subtract these two velocity by time, then you get acceleration with which he is going. That way you can measure. Maybe you can attach something named strain gauges on the material. How quickly it is going to flip the thing, based on that one can measure. So measuring, saying something like velocity is easy. Saying something like position is very easy. But measuring through particular instruments requires bit sophistication. Somehow, if one can really measure such kind of velocity, such kind of acceleration at a given location with the space and time, we call Eulerian approach. There you don't really care about whether red color particle, blue color particle, or whatever. What you do is, I'm going to sit at this location like a traffic constable. I don't care whether it is BMW car is going, or Porsche car is going, or perhaps something like Maruti Alto is going. I don't really care. I just shoot it. I measure the velocity. That's it. I don't even change my location. Just shoot, 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 get the velocities. If I'm going to do that, we call that as Eulerian approach. No, I'm going to sit in the car along with you. If I'm going to measure your velocity from that monitor dashboard, then we will call that velocity as Lagrangian velocity. That time, when traffic constable is shooting you to find out your velocity, and also there is a person in the car simultaneously is measuring the velocity, these two velocities supposed to match. So one is Lagrangian velocity when you are sitting with the car along with that person trying to monitor the dashboard. You have a radio transmitter, immediately you measured it, transmitted that velocity, traffic constable got it, and also traffic constable at the same time shot this laser, try to find out the velocity, he got Lagrangian velocity. These two velocities supposed to match at that given space, at that given instant of time. Is that point clear?
Yes.
Guys, is there any person to whom it is not clear? There are two velocities we are talking about. One is Lagrange velocity, other one is Eulerian velocity. These frames of reference is very important to begin any further things on our fluid mechanics, because formally we would like to really talk in terms of mass. That is the only way we can really communicate. Visuals are wonderful. Something like you are trying to look at something, flow is coming from one location, going away, and so on. Something is rotating. What it means, this rotation, how much velocity it really possesses, how much acceleration it possesses, how much force it really impacts, whether it is good to have it behind the bridge, or is it good to have before that bridge, or does that growth of this thing really going to affect this bridge? These kind of things require formal definition what we are talking about. So for that purpose, what we are trying to introduce is these two frames of reference. As long as once I tag, like this is BMW car, I'm trying to measure only velocity of that particular BMW car, then we call Lagrangian. But I just stationary at a road. I don't care whether it is BMW or perhaps Porsche or Maruti Alto, whatever the car passes on the road. If I measure any car velocity at that particular time and space, we call that one as Eulerian velocity or Eulerian approach. Okay? Fine. The way
Yes, I got it.
okay, wonderful. The way these two things are connected by this relation, it looks like a bit complicated to sense it. What is this capital D by dt? What is this partial derivatives? What is this gradient operator? what is this u in bold colors, what is this u in bold colors, these things require little bit understanding. That is the thing what we are going to really look at. And in most of our fluid mechanics course, we work only on these terms. And these terms are quite easy to calculate, though it looks complicated. And this is Eulerian description. That is equivalent to this term, looks simple, but calculating that, tracking each and every particle is difficult, and that's what we call Lagrangian velocity. This is u is velocity, d by dt of u is acceleration. This is Lagrangian acceleration, for which you can straight away write Newton's equation of motion. In your ballistics and so on, so kind of thing, you might have used small du by dt is same as in fluid mechanics capital du by dt. It is just formal way people have used it. So we are going only with that definition. And these partial derivatives, we require some time to understand. Fine. To understand that, first we have to bring something named analogy or analogous example, especially about car racing. question is, if something like a car races with such kind of speeds like 250 kilometer per hour and so on, what actually matters to maintain that speed? What are the things one should really worry about? If something like on it,
Aerodynamics,
yeah, someone was saying.
aerodynamics and the means like friction coefficient of the tires, like those.
Okay, so the friction coefficient on the tires, or perhaps the friction land to this tire, whatever that friction, and why aerodynamics matter?
Because the spoilers, those are used to basically push down the vehicle. Like if the vehicle at that speed, it might fly off. So
Mm-hmm.
the spoiler is used so that it can means properly press on the ground and give a sufficient normal for the friction to act.
I see. But if where do you find the spoilers? At front or back?
On the back.
But why I should care about back? Why can't it get top or perhaps front or somewhere, or maybe on sides or?
So we work on they work on aerodynamics to reduce the drag, that is the friction caused by the air.
Air, how it actually imparts the drag on the car. I mean, when I'm passing in air, why do I experience drag? The first question.
So the car reflects the direction of airflow. So like
So
there is drag.
car reflects air sideways, but drag is in the direction of the car, right? The velocity
Yes,
with
sir.
which or perhaps the speed at which it is moving. Opposite to that, you will have drag. If that is the case, if air is getting pushed away, why do I experience drag in this direction along the
Newton's
car?
third law.
But pushing
So
air is
because
sideways, right?
yeah,
Like
sir. So
in the
because
horizontal component,
Or am I
the spread
pushing
is.
air forward?
So there will be some
Maybe we are
angle.
moving relative to air, and
Mm-hmm.
so
We
the
are
air is
moving
moving
relative
relative
to
to us.
air. Okay.
Pressure difference might have been created.
What is the connection between pressure difference and drag? Now the question really comes like, is it the difference in pressure forward and backward, should we call it as drag? Or is it something like on the body, on the sides, something like some kind of friction which we don't know how to quantify? What to quantify also we have no idea. Is that what we call drag?
The
Yeah,
pressure difference.
the
Hmm?
friction, the
So the friction,
not the
so,
resistance.
so the friction caused by the molecules and particles of the air.
Okay. So you mean to say that air molecules are bombarding the car and that's going to create friction?
Yes, sir.
Or is it something like air molecules are completely halted on the car? Or air molecules are continuously pulled on the car so that one has to do some work done and that manifests as friction?
The air molecules are completely like bombarding the car, so it will impart some kind of force on the car.
I see. So to define or to even to introspect this terminology, what actually it means, how it really works and so on, the first thing is we have to really come out of this Lagrangian frame or Newton's equation of motion. Why I'm saying is at Newton's equation of motion, we always think about points, particles. Your entire car is strung to a single point, and I can apply something like this is the force, that is the force, and so on. If that is the case, my car is supposed to be a spherical object. It should not have some fancy design. This is the first lesson as an engineer one will learn about it. If Newton's equation of motion all the time we try to talk about center of mass, why this specific design of a car? Why can't it be something like a sphere? Or at most it can be something like ellipsoid. Instead of that, why the hell we really have such kind of fancy ships? It is something to deal with extension of the Newton's equation of motion. I cannot really tackle one point, but multiple zones, areas, volumes, I have to involve in that. Second thing, when we have such kind of thing, maybe forces I can really write at each and every point and so on, or maybe collectively at center of mass. Why car is withstanding such kind of huge forces? It could have compressed, squeezed. The metal sheets can really fly off. But without that, it is still in a position to withstand. That means internally some kind of mechanism is trying to hold them. We can say that we are doing welding, we are stuck to that, this is material have some strength and so on, so kind of stuff. But how those things are really possessing? When you are applying force, what is making not to accelerate the system? What is not there to really crush the system?
Sir, proper angle of attack.
And how that really sensed by that material throughout each and every point. For example, if I am going to take a pen, if I am applying equal and opposite forces, is supposed to be at rest by Newton's equation of motion, right? If I am taking a simple pen, a refill, maybe a page, whatever that, if I apply equal and opposite forces, the center of mass always be rest. It should not really go any other places. Maybe even there is a tiny variation in these forces, the point of application and so on. At most, it can really create movements or accelerations to go there. But if you are going to cross certain limits, it can really bend the material. It can even crush the material. Like take a piece of chalk piece, try to apply torque. It can really twist forever. But instead of that, it is trying to break at one point of time. How materials really responding to that? Is it just at center of mass do I have to really worry about? Or throughout the system do I have to really worry about? That kind of extension requires your Eulerian framework. You cannot straight away work on Lagrangian framework. You have to really think about all that three-dimensionality, not only in terms of x, y, z coordinates, but even in terms of time, one has to really worry about that. Though force, point of application, you can really talk about it. Somehow it is transmitted to center of mass through the three-dimensional object. Now let me ask you a simple question to begin with. You must have seen simple problems like a tube, cycle tube. It can be tire also. Where is the center of mass for this tube or tire?
At
In the center.
In center.
The center.
Here. So if I want to roll it or if I want to displace it or perhaps whatever that, where exactly I need to apply the force? Force by definition. What are the characteristics of a force?
It has a magnitude and direction.
Direction. So that's the reason I am using this underscore notation. So this terminology also we have to learn while we are going. If I am writing on page and other kind of thing, tab and other stuff, if I put underline, that indicates that it's a vectorial quantity and it has three components, at least for our science courses. Maybe in x direction, y direction, z direction. If I am writing on the textbook or whatever that, what usually people do is, because they don't put underline, they write it bold letter. These two notations are equivalent. This is bold F and this is underscore F. Both have same meaning. Both are vectorial quantities. Textbook usually do not prefer that underscore or cap. One can write even arrow. One can even write something like cap. But typically, as you are going forward in studies and so on, the common terminology to use this kind of vectorial things is this kind of underscore symbol at notes levels, and at textbook levels you will find these bold symbols. So we realized it has three components. So if I want to make this wheel to roll, where exactly I'm supposed to apply this force? If I want to displace it, where to apply? Can I write F is equal to ma equation for this rolling thing, or maybe sliding kind of thing? Hello,
Yes.
Yes, sir.
I would like to apply F is equal to ma. Where to apply that? If it is sliding,
We can apply anywhere.
anywhere? You mean here?
No, it's on the tire.
On the
On the
body.
tire you want to apply. But where do you write this F is equal to ma equation?
For the center of mass.
Precisely, most of the time we describe if it is accelerating, decelerating, moving with velocity, somewhere here we write equation of motion. F is equal to ma. Is the tube there? But still you write F is equal to ma. But if you precisely apply on center of mass, will this tube ever really rolls?
No, sir.
Then why we are applying that? How to understand this
Is this tube kind of
paradox?
fixed in the center? Is this tube fixed in the center, or is it like on some surface and is about to roll on the surface?
You want to put something like a bottom free? Fine, no issue. You would like to really keep it.
Yeah.
And now what you are trying to say is, hey Raja.
And if we put our tube on the on the surface, then if we apply F at the center, it will move, right?
Where should I apply force?
At the center of mass.
Center of mass where? I don't know.
Like at the center of mass, along the plane.
You mean this is the center of mass, the blue one?
Yeah.
If you apply force on the center of mass, will you be in a position to really move a tire tube?
Yes.
If
Because
I give you really a tire, no, I mean, question, don't worry. I mean, I'm not actually trying to tease you, but I just want to ask myself this question to really understand all the time what actually I'm trying to learn about this science. So it's not meant for you, but Raja is asking himself this question. If Raja has been given a tire, maybe he goes to a garage, he takes a tire. He knows where is center of mass, just tire, no connections, nothing. He applies force precisely at center of mass. Will he ever be in a position to roll that tire on that platform? Will he ever in a position to tangibly see that effect?
okay, there must be some kind of hook connecting the center to the tire.
One at a time. Name yourself and we will interact and learn it together. If I just go to a garage or perhaps take my tire, literally speaking tire, not the wheel. Take tire. I know where is center of mass because it is a circle, center of mass I know, but I don't see any material there. It's completely air. I apply force there, whatever the direction. Will I ever be set this tire into motion?
No, sir.
We cannot, right? Now, where is that problem really comes in terms of applying F is equal to ma? It is nice to know the formula, perfectly fine. On center of mass, this force might be acting so that it is going to set into motion. This is perfectly fine for +2. But if in reality, if I really go and apply there, I may not be in a position to really set into motion. Somehow, I may have to really bring material at something. Maybe one spoke, maybe this one, maybe this one. Somehow I need to really connect it. Unless I bring material there, try to really put it, maybe apply there, then I may be in a position to really set into motion. Right? That means material becomes very important in terms of application of forces. If material is not there, you will not be in a position to really set that. This is the problem. The 17th century, 16th century guys, 16th, I mean like 1700s to 1800s guys really face the problem. Hey Newton, you really formulated very nice kind of theories and so on. Leibniz also tried to really work out, and you guys fought with each other, try to develop some theory, write F is equal to ma. You're in a position to describe, but we are coming across this kind of problems when material is not there. You all the time talk about center of mass, write down the forces, movements, wonderful. You do that, it is perfectly working. But how I will really in a position to really set that tire into roll unless I bring that material? Your equation of motion never describes that. What I am supposed to do? How I will be in a position to really extend your framework to generalized materials? Then they come across something named a field rather than center of mass like point, something named stress they try to introduce. You can define stress only when material is present. When material is not present, there is no stress. It's not the other way around. Whenever stress is there, there should be material. If material is there, there may be stress, there may not be stress. That's a different story. If I can introduce something named stress, your Newton's equation of motion, I can rewrite it in such a way that in terms of those stress terms, I can still apply it. I can handle any problem as long as I can really define this kind of field stress. That is the one what someone was pointing out. What is this kind of terms? Though this is not a stress term, but equivalent kind of terms, we are going to write it. So let me further introduce that before introducing Lagrangian. We'll again come back to that. Now let me ask you a question. If I want to really define an area, this is tire, I'm just rolling, or perhaps a disc plate, a circle is something like a disc, a circular one. I want to define what is the area. How will I calculate that? Any idea? Hello? Guys, say something.
Pi r square.
Yeah.
Pi.
Maybe if it is a circle, pi r square, you will calculate. If it is having some complicated shape, maybe you try to bring something like differential calculus, define the coordinate systems. Maybe Raja, first we have to really define what is x-axis, what is y-axis. Then you put your object. It should be well-defined object. It should not have any fractal structure. Then you pick something like what is the coordinate, take some strip, span that strip, you will get area. Right? Hello?
Yes, sir.
Yes, sir.
Yes, sir.
Wonderful. If that is the case, let me ask you. In 3 dimension, maybe I'm going to keep my circle on the xy plane. So z plane is perpendicular to that. In some cases, I'm going to keep my same circle in that way, inclined with the z axis. So it looks like ellipse. Maybe in some cases, I'm going to really keep it in the z direction. So it looks like a line. You understand what I'm trying to draw? A circular disc I have taken. Sometimes I'm going to keep it on the horizontal plane, sometimes inclined, sometimes something like vertical. I'm trying to visualize these areas. In all these cases, I will see different kind of areas. So usually people come up with a strategy. If you are going to define area, it's always be a good idea to even point out which direction this area is facing. So usually people try to really define why we are trying to say that. Also, we will come back to that. If someone is saying area, it's okay to say that, but they would like to really have orientation of that area also, especially in mechanics. Why? Because when you want to really set a tire to roll, it's not only center of mass you would like to really know, because now you are going to really create forces on that system or maybe stresses on the system. How this tire is oriented also important. Whether you would like to apply center of mass in that direction, whether you would like to apply center of mass in that direction, or whether you would like to apply something like a three-dimensional field, this direction, that direction, that direction. How you are going to apply normal to that area, tangent to that area, these things also people are interested to know. Why I'm saying is, for example, let us take something like, how about this hanky? Can you see my hanky?
Yes,
Yes,
sir.
sir.
Yes, sir.
Now it has one particular area. Let us assume that it is two-dimensional object. Though it has some fabric and so on, so kind of stuff, let us assume that it's rectangular plate. Now you would like to apply forces parallelly in this direction. I'm trying to stretch it. Okay. Where exactly I'm going to apply these forces? On the material. If I'm happening to apply this, I'm going to apply on these points. But finally, where exactly it is manifesting? It is manifesting at center of mass here. All these forces really go from center of mass. Is it going to really stretch it? But in reality, where I'm applying is not center of mass, maybe at the ends. But entire material getting stretched up. Same thing, I can really compress it. Maybe if I'm taking something like a book, trying to apply in that direction, I can really compress it. The same thing, I can apply it on points, but entire material is going to subject. Now, the same forces I can apply, one on the front, other on the back side also. So this is my direction vector force, the fingers pointing. One is that direction, other one is on the back side. Okay, I'm trying to do that. That's also I'm applying forces. Again, that will manifest on the center of mass. But in both the cases, when I'm trying to apply here, it is different behavior. When I'm applying here, it is different behavior on the same two-dimensional system. I'm pretending it's to be two-dimensional. When I'm trying to apply, it's completely different effects is going to give. Even on one-dimensional system, when I'm going to really look at it, something like pen. I can stretch it at point, I can compress it, I can do something named shear also. So forces, where exactly I'm applying, not only points, but something like on which planes it is acting also becomes important. So usually in mechanics, to handle this kind of complicated scenario, people try to introduce that, see, end of the day, you are going to apply forces. Maybe they will be manifested on areas, which planes, areas you are going to apply. That is the one overall going to change this entire deformation. Maybe your racing car pierces through air. Maybe your submarine is trying to pierce in liquid. You might think that it is just force acting at one point, but that is subjected on the entire surface. That is the one which is trying to divert your liquid. That is the one which is trying to divert your air. That is the one which is trying to stretch air. That is the one which is trying to stretch, compress your water. This kind of variety of effects are happening. Maybe even for materials, when I am going to apply force at this point, force at this point, it may not just compress, it may buckle also. Buckle means if you take a steel plate, try to apply the thing, forces, collinear forces, still you can really set into one directional thing. It bends. Like soda can, you take it like if you are drinking Monster drink, Red Bull, whatever this kind of thing, the can, you try to apply huge force, it buckles. Same forces, though supposed to act at center of mass, they are going to generate different effects because they are subjected on different planes. So usually at mechanics, to handle such kind of things, what people try to do, you can see my screen still, right? Guys,
Yes, sir.
what they try to do is tackle or track even areas, not only in terms of magnitude like meter square, but also give direction. Direction always be normal to that plane. If it is circle, maybe the direction of circle is a two-dimensional object, so the normal direction always be perpendicular to that circle. Maybe you have a three-dimensional object. You have considered something like a surface. I bent it. Normal at this point, normal at this point, normal at this point, normal at that point, normal at that point. So on the plane, you have normals varying. So if I want to really define something like area, same thing. This area also one and the same. I'm not going to stretch it. Let us assume it in that way. Now the only difference between this one and this flat one is the direction of the normals. How those normals are going to really vary, based on that I will be in a position to really define something like areas. So what people try to do is, area is also a vector. It has functional form, maybe x square y I plus yz sine x j plus maybe z square log z k. Maybe it depends on the what kind of surface you are going to span in the three dimensions x, y, z coordinates. You may be having A as the area of that surface every time you have some normal. Now on that, because we want to generalize rather than really looking at simple things, if I am going to really look at simple thing, it is very nice to handle it. But whenever difficult things like a tube, center of mass I need to apply, but I cannot really set into motion, it becomes a paradox. To explain that, one has to really make it a generic framework. And that generic framework, what we are going further. First thing what we want to really do is, before even defining something like acceleration, I would like to really define force. To define force, because of this paradox is like when material is not there, still it is going, I need to define stress and so on, so kind of components. So that's the formalism what we are trying to bring in this class. And force is also a vector. It might be having different kind of components. You might be having xi plus z cos y j, depends on which points you are going to apply on the entire material. You may not have to apply it only on the center of mass. Some points you are going to apply. At each point, you will have variety of distribution of forces. Maybe your car is piercing through air. Each of that surface on the car subjected to different kind of force. And that based on where exactly x, y, z coordinates, I'm just prescribing it. Whether that happens on the car or not, that's a different story. But I have a formalism. Each and every point on that surface, where surface is defined based on some origin, x, this many units of x, this many units of y, this many units of z, and the direction in which it is acting. Maybe something like x squared z k bar. This is the way first people try to define it in that 16th, 17th century, to make it more formal way of looking at Newton's equation of motion. Any idea about stress? Did you ever come across that term? Hello?
Yes, sir.
Can you tell me? Hello? Guys, tell me
Thrust
from
per
your plus
area.
2. So what we have learned in our plus 2 kind of science is maybe stress is defined as force per unit area. That means if I go back with our plus 2 definition, I take some material, it has some small thickness, you apply something named force. Where should I apply? Here. But in principle, according to Newton, it extends all the way to center of mass through material. Maybe the other side fixed. So reaction force might be there. This end is fixed. So if I am going to write free body diagram, I have to really chop it off, try to see how forces really act. That's also subjected to equivalent reaction force if I open it up in terms of free body diagram. What is the area I would like to really look at? Can you tell me? Hello? Force per unit area, if I would like to define more in terms of plus 2 kind of science, can you tell me which area I have to really consider?
Area of cross section.
Area of cross section, or here the black color shade what I have shown, right?
Yes, sir.
Yes, sir.
This is the one. And I will be in a position to really define F bar by A as stress. Now the same situation, if I am going to ask you, the same material, same, but my drawing looks a bit ugly. Again, it is connected rigidly here. Now, I don't want to apply force on that plane. So, this is that direction, but I would like to apply in this direction, perpendicular to that. How to define stress in this case? Which area I have to really consider?
So same area.
Same area, wonderful.
Yes, sir.
Okay. Now let me take one more example. It takes some time to really define these things. All we need is little bit patience and tolerating Raja for some time. Now I'm going to apply neither in this direction nor in that direction, but somewhat inclined to that. It's not third dimension of Z, but somewhat inclined to that plane, x-axis, y-axis. How to define stress?
So
we have to break components of this force.
So you will break down that into this component and this component and define what is this component Fx by A, what is that component Fy by A. Is that right?
Yes, sir.
Now if I have three-dimensional force, I will end up even with Fz by A. Hello?
Yes, sir.
Yes.
Yes, sir.
So
Yes,
this, okay, if that is the case, let us fix with Fx, Fy, Fz directions. So the force what I'm going to apply is Fx I cap, Fy j cap, and Fz z bar k. This direction I'm fixing. Now I'm going to change the plate orientation. Right now, plate is aligned in the direction of x-axis, or if I'm going to really define the normal vector to the plate is in that particular, what is the direction? If this is x, this is y direction.
Y.
The plate is aligned in the y direction because I want to really say area. Rather than saying horizontal, I'm going to describe in terms of normal vector. The plate is oriented in the y direction and force can be three-dimensional. I'm going to define that. But now I'm going to ask you a simple question. You have already defined something like stress. This is also stress. This is also stress. This is also stress. Though you call something like normal stress, something like shear stress, something like some other kind of stress and so on, so kind of thing. But in each direction, you are going to say that I have some kind of force per area. But now what I'm trying to do is, why my plate has to be like that, but I'm going to really flip the plate tinily. I can reorient plate also in that direction. I can orient plate in that direction also. That means my area, whatever the direction it is showing, that itself I'm going to reorient, but not the force. Will these components really changes or will it really gives me any extra components? Does, or let me put it in this way, does the orientation of plate also matters? Or only the cross-sectional area matters?
Yes, sir. The orientation matters.
So this is the problem what actually the 16th century, 17th century scientists really face. Even Newton's equation of motion is wonderful, Baba, F is equal to ma. But when I'm going to really work at materials, center of mass, when there is no material, I cannot apply, I cannot accelerate the system. I need material to really put it. First problem. Second problem, now you nicely apply like force. I know how much area it is acting, whether the material really withstand those forces or not. You say that infinite forces which accelerates to infinite acceleration, but in reality, that's not going to be possible. Materials going to break into pieces. Maybe on liquid, your torpedo is trying to shear the liquid. The kind of speeds it goes, the water can really shear, it generates a lot of temperature, it vaporizes, entire liquid disappear like vapor. Maybe your racing car is trying to pierce through air. It generates a lot of heat. Maybe your material can start melting also. Extra physical effects really coming into picture. Maybe your space vehicle like re-entry vehicles entering into Earth atmosphere. The speeds at which they are really coming, they can really break into pieces. They can ablate. You cannot really handle just stupid Newton's equation of motion, but you require lots of corrections to that. That is the place where the 17th century guys really started wondering, man, this thing we have to really understand something like this definition force per unit area is not going to work. We need to generalize it. Now my plate is like this. When I am going to apply the forces, it shows one kind of stress. If it is slightly oriented, now it have two kind of component, extra component of stresses coming into picture. Now when I have three kind of stresses are coming into picture. Now plate is also reoriented, extra kind of components are coming into picture. We need generic formalism. That is the place where they have introduced stress is not that easy definition like force per unit area, but introduce something named stress tensor. You know what is a scalar? I mean, I'm sorry, because to understand Lagrangian accelerations and so on, we need to understand the tensorial notation. Without that, something like grad u, we will never be in a position to really understand it. And for that purpose, first we have to really go define these extra mathematical things, object quantities. Once we are comfortable with that, then we can really visualize these hyperspaces, like higher dimensional spaces, then think about and come back. That is the way we are heading for. Now, force is a vector, area is a vector. Maybe can you tell me other vectors, what you know? Hello.
Velocity, acceleration.
Acceleration, let us write it A bar. What else?
Velocity.
Velocity, U bar, let us assume it. What
Momentum.
else? Momentum, maybe something like, let us use a word J, and so on. Now, I'm going to ask you, can you give me some scalars?
Sure.
Pressure, fine. Can you give me some simple examples which I can really sense it?
Temperature,
Mass.
Temperature, fine. Wonderful. What else?
mass,
Mass. What else?
Volume,
Volume. Let us use that symbol. Volume.
distance,
Fine. Now, let me ask you some other thing. Can you tell me what is the value of 1 by 2?
0.5.
0.5, fine. What is the value of 2 into 3?
6.
6,
6. Wonderful. What is 2 plus 4?
6.
2 minus 4?
-2,
Wonderful. For scalars, is very well defined. Division, multiplication, addition, subtraction are there. Now let me extend this similar kind of thing for vectors. Can you tell me I plus 2j minus 3k, k for this, minus 2i plus 3j plus 4k? What is the value?
Minus I minus J minus K.
minus I,
Minus
Minus I
j
minus
K.
J minus
Okay.
7K.
Minus 7k. Very well defined in terms of subtraction. Addition also you can do that, right? If you do addition, you will again get something like I, J, K kind of combination. Is that fine?
Yes, sir.
Now what about multiplication of I plus 2j minus 3k and 2i plus 3j plus 4k? I just want to multiply. What I'm supposed to do?
we have to define cross product or cross product.
So you might be going to begin something like either dot or cross product. You require additional definition. When vectors you are going to play with, it's not that kind of easy multiplication what you have done for scalars. You define there are two kind of things. If I'm going to use dot product, the vectors are condensed to give me a scalar. If I am going to really use inner product or dot, I'm going to condense vectors to get me a scalar. So 3 components become 1 component. If I am going to use cross product, do I see still condensation of 3 components? What do I see? How many components I will get?
3.
3. It's not going to condense, it still preserves the number of components. One question. Two questions you have to answer. So the first question, Raja, you are saying like inner product, you are going to do some kind of condensation to make 3 components into 1 components. You are in a position to really preserve those components to maintain 3 components. But is there a product which can increase 3 components into 9 components? That is the first question. Without really worrying what it means, as of now we are switching off science, trying to ask question like an algorithmic point of view. Scalars, addition, subtraction, all these kind of defined, wonderful. Now I want to really begin vectors addition, vector subtraction, and so on, vector product also. Then naturally I come across like there is a way like inner product, cross product, but is there a product where I can increase the number of components? That's one question. One second.
We can define new
Let me pause.
components.
Let me pose the question. That is the first question. And second question, if I am going to take two vectors, can I really do division? Is that possible? These are the natural questions one has to ask. Now go ahead.
So for the first question, like if we represent our vector as a 3 cross 1 matrix, we can take a 1 cross 3 matrix and multiply it with it to get 9 components.
Wonderful. What's your name, sir?
My name is Mohit.
Mohit. So what Mohit is saying, hey Raja, forget about science, but as of now, just a mathematical point of view, if I am going to really talk about it, I have two vectors. Let us call A1, A2, A3. These are the components. Or I, J, K. Maybe I have B1, B2, B3 kind of components. Again, I, J, K. Now I just change into square brackets. If I would like to have inner product, then A1, B1 plus A1, A2, B2 plus A3, B3, I'm going to get as dot or inner. If it is cross, then naturally I will be going to do A2, B3 minus, what is that? B2, A3. The second component is reversing the directions. So reversing the directions means B1, A3 minus A1, B3. The other component is A1, B1, A1, B2 minus A2, B1. This is what we call cross product, right? What Mohit is saying, hey Raja, maybe I can think of a freshly new way, right? A1, A2, A3. It is 3 by 1. B can be kept like B1, B2, B3 as 1 by 3. Now you go ahead and fill the things. A1, B1, A1, B2, A1, B3, A2, B1, A2, B2, A2, B3, A3, B1, A3, B2, A3, B3. One can really write it. What is wrong in that? Why can't I write it? Now I'm going to increase the system. Whether that has meaning or not, that's different. At least algorithmic point of view, I can really construct this natural product. Right? Hello?
Yes, sir. Yes, sir.
That kind of products, in case if we are permitted to do, we call dyadic products. Did you ever heard this word? Or is it first time?
First time.
Okay, fine. No issue. Why that becomes important, shortly we will see with the second question. This is one way, but is that the only way or the other ways also there? Why, Raja, you have to really multiply? I will multiply, I will reshuffle the things and get it. You can do that. But what are the general ways? One of the thing what people try to recommend is this kind of dyadic products. Whether that makes any sense or not, that's different story. But at least at math point of view, it's okay. Now, let me ask you second question. Other than Mohit, how to do this division for vectors? I plus 2j minus 3k by 2i plus 3j plus 4k.
Denominator.
Huh?
Dot product on both numerator and denominator with the denominator vector.
Am I permitted to really do dot product at the bottom and top? Why I should do that? Why not cross product? If I am permitted to do dot product, I should be permitted even to do cross product. What is so special about dot product there?
Actually, we are this division actually signifies multiplication of reciprocal of the denominator term.
Does a reciprocal exist for a vector? What it means reciprocal of a vector?
So we can define it, right? It's our
How?
wish.
Okay, let us bring something like a science. Acceleration is a vector having so and so kind of thing. Force is a vector. What it means reciprocal of a vector, what it does, is it going to compensate that vector? Force, subtraction of other vector, then subtraction is there as reciprocal. Force there, force has to disappear. I will apply counter force. So subtraction, addition are well defined. But what it means reciprocal? There is a problem for vectors. No, Raja, that doesn't matter. I'm just casually defining it. If that is the case, why only dot? Why not cross? This kind of new problems naturally arise.
Because we have to make denominator a scalar quantity, so we will multiply. We will do dot product.
But why I should really make denominator as a scalar? Is it something like a rule? I forcefully, Raja, by any means, I need to define something like a division.
Sir, vector in denominator will be inconvenient.
Vector
Sir,
in,
if it's a scalar, then we can divide the denominator among all
precisely.
the
So
numerators.
if it is a scalar, what's your name, sir?
Priyanshu Nanda.
Priyanshu. So if it is something like scalar, I have no problem. 1 by 2 I bar, 2 by 2 j bar, minus 3 by 2 k bar. There is no problem. I can straight away do. But if it is something like a vector, I cannot just restrict myself to something like multiply denominator and top side, like a complex analysis, complex conjugate, you multiply it. That kind of rule is not defined for these vectors. This division is not obvious. If you are going to say that I'm going to do dot product, you are supposed to permit it to do even vector product. There should be a generalization. Then you should be in a position to even do division with the dad's. So there is a problem. So what people try to do, because it's mass, it's not something like God's given gift. We are the ones who are trying to put axioms. So what people come across is, well, if that kind of division is there, maybe I can do something like a clever trick. A division, I won't define it in a very nice way, but in a better way, I will define something like a force vector. I would like to get F1, F2, F3 components. To do that, what I am going to do, I'm going to write a matrix kind of structure. I will introduce formally dot always exists. Again, we will come back what is initial notation and so on. If I can introduce in this way, this division problem, whether I should divide with vector, whether I should divide with scalars, should I divide with tensors like diodes and so on, that problem can be eliminated by introducing something named tensor. The more formal definition is second rank tensor, having an inner product dot with a first rank tensor, or more commonly known as vector. So I introduce a terminology named tensor, describe any kind of thing, whether scalar, vector, second rank, third rank, fourth, fifth, and so on, so kind of stuff. I don't really care. I all the time use a word tensor. If something like 0 rank tensor, it is just a scalar, one single number, 0 rank. If I am going to have 3 components, whether I write it in vertical, whether I write it in horizontal, it doesn't matter. 3 components is supposed to have. Then we will call as first rank. And if it is going to have 9 components, whether I write it like a matrix, whether I write it everything in a single column, whether I write it something like one single horizontal row, it doesn't matter, but it's supposed to have 9. Maybe for writing aesthetic aspect, it looks nice for my eyes. I'm going to write it like matrix form. The indices, what I'm going to write, 1, 1, 3, 2, 3, 3, is for computer terminology. It's easy to define something like A of I comma j. Maybe in your C programming, A of I comma j. I varies from 1 to 3, j varies from 1 to 3, then I will get A11, A12, A13, A21, A22, and so on. This is what we call second rank tensor. The advantage in defining, if I would like to define third rank tensor, can you tell me how a third rank tensor really looks like? Hello?
Yes, sir.
Can you tell me?
So A1112, A1113, and then
And
we
so
will
on.
have
So how many components it will be having? If I, J,
27.
K are
27.
27.
So maybe
20.
the easy visualization is
Q.
just for visual. That doesn't mean that it has to be cube. I just have to fill elements in that. I can really put all these blocks side by side and go in a consistent manner in one single line also. Something like this. It doesn't matter as long as I know what I am trying to do. Just for visual point of view, easy compact form is this. The computational programming or whatever form is this. This is third rank tensor. Does it have meaning or not? That's a different story. This meaning always comes when you are really facing a problem. Because we face a problem with Newton's equation of motion like force, we went ahead, try to define something like there exists something like a higher dimensional quantity, stress. That is the thing what we are going to define now. If we never really face that problem, we are happy. Your life always begins at the end of your comfort zone. And that is the thing what we are trying to do. Because we faced a problem with force, division with area division. That's the thing what we schematically try to look at. Force has 3 components. Now area also flipping in different direction. Defining this division is non-trivial task. And in each of these cases is different. But I would like to have a general framework. For all the cases, I can define just simple thing which can gives me different meanings. That kind of condensed information requires this kind of product. A 3 by 1 components, if I would like to really get, what I am going to do, 3 by 3 second rank tensor, condensing dot means the word condensing onto 3 by 1 vector. So 3, 3 goes off and it gives me 3 by 1. If that's going to happen, I use this symbol dot inner product. The same, now I can generalize this also. Now I have something like a vector A1, A2, A3. How it is going to do that, we don't care, but it is going to apply on another vector. Dot means condense. A1 condensing on B1, A2 condensing on B2, A3 condensing on B3. So the definition I have to do AI, BI. For I is equal to 1, 2, 3, A of I. So let us learn it more formally. So I'm just writing a pseudo code. I'm just writing a pseudo code for I is equal to 1, 2, 3. For j is equal to 1, 2, 3. Because 3 dimensions we are playing with XYZ coordinates. A dot B means A dot B is equal to A of I multiplied by B of I over summation. So A dot B end A dot B is equal to 0. Can you see the pseudo code? If this is clear, any mathematical operation by hand we do becomes easy. A vector dotting with B vector means this is the operation what I have to do. Can you read the code?
Yes, sir.
So, if I want to use mathematical notation for that, I'm sorry, this is not zero. If I want to really write mathematical definition, is summation A of I, B of I is equal to 1, 2, 3. This is the definition of inner product or a dot product. Are these both the definitions are clear to you? One is your pen paper kind of definition, typical mass. Other one is computational way of looking at the dot product. Are they equivalent?
Yes, sir.
Are you going to
Yes, sir.
get the same number if you do, if literally if I am asking you, can you really calculate inner product of two vectors in your general way, what you have learned, the computational program pseudocode and the summation symbol what I wrote, are they equivalent of each other?
Yes, sir.
Go ahead.
Why are we using loops here?
We don't require, precisely we don't require. So basically to define inner product, we don't actually require this thing at all. This itself is good enough. That is the way we define inner product. Good catch, Shaumili. Now, why I have to use only I? I can even use J. Still, I will get A dot B. The meaning of that, computationally, what we have seen, mathematically, what you do on pen and paper, usually people represent by symbol in this way. A textbooks and so on, if you open it, A dot B is summation I is equal to 1, 2, 3, A, I, B, I. It can be I, it can be even J. Is that fine?
Yes, sir.
Is there any question by others? Hello? No. In shorthand form, people even write it. Why even summation symbol I have to use? A dot B is equal to A I B I. I don't want to even use summation for ordinary calculations. Whenever two indices are same, I mean this is the one. They are one and the same. That kind of form Einstein has introduced. Albert Einstein. And this kind of notation, not showing summation, is called Einstein summation rule. It's just language, but the meaning is that. Okay? Hello?
Yes, sir.
Yes,
If
sir.
that is clear, now my next question really comes into picture. Typically, textbooks or notes and so on, so kind of stuff. If I am writing A, going to write this, it means first rank tensor or a vector. If I am going to write, this is what you call second rank tensor or your tensor, and so on. This is second rank, this is first rank, and this is zero rank, and this is higher rank like third rank, and this is fourth rank. And this one have only one element, this one will have three elements, 3 power 1 rank, this will have second rank, this will have third rank, this will have fourth rank. That many elements you will see. Because you handle XYZ coordinates, you have 3. There are some components, n dimensional components. Then your 3 has to be replaced by that number n. I will tell you one example. Why, Raja, we are going to learn about all these things? Because future courses, you are going to learn something named transport phenomena, advanced fluid mechanics, CFD, and so on, structural mechanics, solid mechanics, and so on. This becomes fundamental basis. You must have learned something about thermal conductivity, right? Can you tell me thermal conductivity value for copper or gold or whatever that? Is it a scalar?
Yes, yes, brother.
That is the thing what you learn in +2. But when you are going to learn future courses, you will be actually introduced thermal conductivity is not a scalar, it is a vector, it's a tensor. It's a fourth rank tensor. You can simplify it to second rank tensor. Because materials behave isotropic, homogeneous, and so on, so kind of thing, you will get one number. The Fourier's law of heat conduction, what you have learned, heat flux is equal to K multiplied by A multiplied by del T by del X. The del T by del X in 3 dimensions become del T by del X, del T by del Y, del T by del Z. That means heat flux, not a scalar, it becomes a vector. Now area is also another vector. So to condense this, your thermal conductivity is supposed to be fourth rank tensor, because there is a gradient operator, there is something like area, there is something like thermal conductivity. So you, based on material, it becomes fourth rank tensor. You condense it to finally reach vector. That is the thing. The next question what we are going to really ask ourselves. I said something like, hey Raja, force is a vector, area is a vector because of orientation and so on, and we cannot have vector to vector division. We need to introduce higher dimensional object. We have introduced something like an object of rank 2 and introduce something like dot product. Then I will get 3 by 1 component. Can you tell me computationally how to write this?
F, like Fi equals to T of I j k into Ai.
Do you have T of ijk?
Like I would, like T.
Go ahead, try, give a try.
And it's multiplied by Ai. Like Tij, I'm not able to. Like Ai, maybe. It's like T11A1
Okay.
and T12.
The easiest way is Because inner product we want to really do. First write I comma j. This defines T. Right? Because it's a second rank tensor. You will be going to have how many components? 9 components. Tij describes it. Right? Hello? Yes?
Yes, sir.
Wonderful. Now I would like to introduce star. It's just ordinary multiplication. What I want to really do? I want to have a product. What kind of products I would like to have? When I'm going to shrink it, condense it, Tij and A vector Ak, two of the components supposed to be get condensed. Maybe this one and this one supposed to be condensed.
So are you writing the pseudocode?
I'm going to write pseudocode. So
wouldn't that
basically
be
what I'm
helpful if
supposed to
we
write is Tij star Ak I need to do. However, I need to condense that. That means the loop really comes here. This I need to condense. So maybe f of I end loop for sometime back we have written k is equal to 1, 2, 3. For j is equal to 1, 2, 3. For I is equal to 1, 2, 3. And supposed to be written, but two of the components I would like to really condense. So naturally k, no point in writing k, it becomes j, and one
Yes,
of the
sir.
loop I can really remove it. Bring this one. So first look at the first loop, what we have written. Every Tij starring Aj gives me only T of I. I is fixed. J is going to 1, 2, 3, 4, and so on, so kind of stuff. I'm going to have that entire condensation happened by this. Now I bring this one here, bring this one here, and define f of all i's is equal to 0 for I is equal to 1, 2, 3, end. If I do that, I'm condense the information. The same thing, Mac, is that clear to everyone? What we are trying to do, condensation means?
Yes, sir.
Yes, sir.
That is the one. If I want to really lay down it on the sheet, what I have to do? T11, T12, T13, T21, T22, T23, T31, T32, T32, this entire thing dotting with A1. So let us write subscripts. So it becomes A1, A2, A3 matrix product. I would like to write to get F1, F2, F3, nothing but T11 A1 plus T12 A2 plus T13 A3 T21 A1 plus T22 A2 plus T23 A2 T31 A1 T32 A2 plus 333 A3. If I do by pen and paper, this is the way I do condensation. If I am going to use dot product pseudo code kind of thing, what I am going to see, first you have to keep I1, that is first row. Let us compare the pseudo code and the first row whether they are one and the same or not. So when I is equal to 1, I'm going to look at this one. Just 1 minute, I'm done. I will close the matter.
Sir?
So yes, sir.
So it's 323 into 83.
Okay. Thanks. So let us look at the first row. When I is equal to 1, what do I get from this pseudocode? That I'm going to write it in red lines here. When I is equal to 1, I have to go into loop. For j loop, for j is equal to 1, 2, 3. So T1, 1 multiplied by A1 plus 0 when j is equal to 1. Now j is equal to 2. So this what we are calling F1. That has to be repeated. Now F1 becomes T11 A1 plus T12 A2 is equal to F1 still, because J loop is not finished. When J is equal to 3, you have T11 A1 T12 A2 plus T13 A3. That becomes F1. Loop is done, so you have calculated F1. This is what we call F1 at program. You understand the logic, how we are slowly building up in terms of higher rank tensors. If they condense somehow onto lower rank thing, you will get low rank tensors. Then I can formally introduce something like force means this. Force acts at a point because on those planes stress exists at every point, and stress is not a scalar value like Newton per meter square, just one value. It has 9 by 9 components. That means you take your plate. You may think that at this point I'm going to apply force in whatever the direction. But this point, if you are going to zoom in, any point, that infinitesimal element, maybe on Cartesian framework, looks like a cube, infinitesimal thing. That entire force acts through the center of mass, but that's actually distributed on this plane, on this plane, on this plane, even on the back one, this one, everywhere, somehow in some other form, which we call stress tensor, actually manifested in that way. If I am going to really project those components T11, A1, T11, A2 and so on, A1 is basically A1 of this area, A2 of this area, A3 of that area. Somehow it manifests on all those kind of stuff. Suitably, if I am going to condense, equivalent force I will be going to get. Saying force is easy, but distributing force means actually it went into higher dimensions. If I can do that, I can define stress tensor. So once this stress tensor is defined, if it is going to project onto areas, you will get forces. Once forces are created, then you will have accelerations. Once you have accelerations, you will be in a position to really define what kind of frames of reference we are going to talk about. Okay? Just give me one more second. We are done. So now if I am going to write f I is equal to summation Tij double summation index Aj, where j is equal to 1, 2, 3, I is equal to 1, 2, 3. The easy Einstein notation way of writing this is, because there is summation already for double indices, whenever double indices are there, this is the way we write it for Einstein way. First rank tensor, second rank tensor, first rank tensor. Dot is already replaced by that summation. If I do that, I'm going to get this condensation. Now let me ask a question, pose it and call it a day. Next week you answer me. Instead of this double product, inner product, if I am going to have, what will happen? This is going to shrink it to first rank. From second rank, first rank, I'm projecting it to first rank. If I would like to have increase the order with A, what I am supposed to do? How I am going to increase that? How many components I am going to get? What kind of products or combinations I can really get? First, get that clarity. And we will catch up in the next class.